copy this song for free. For unlimited free songs, dial 567. BSNL connecting. താങ്കൾ വിളിച്ച വ്യക്തി ഇപ്പോൾ കോൾ സ്വീകരിക്കുന്നില്ല. ദയവായി അല്പസമയത്തിന് ശേഷം വീണ്ടും വിളിക്കുക.
In 1755, Benjamin Franklin, curious about the workings of electricity, began testing various hypotheses. In one of his experiments, Franklin took an electrified silver can and dangled an uncharged cork ball attached to a non-conductive silk string into the can. The cork ball was not attracted to the interior of the electrified can. Puzzled, Franklin withdrew the cork ball from the interior of the can and instead brought it close to the exterior of the can. The ball was immediately drawn to the can's exterior surface. How could the same electrified can attract a cork ball from its exterior but not its interior? Franklin never discovered the answer. Fast forward about 80 years as the workings of this puzzle started to become clearer. In 1836, English scientist Michael Faraday made a similar observation to that of Franklin. When charged, an electrical conductor, like Franklin's can or a metal cage, would display that charge only on its exterior, not on its interior. To further test this observation, Faraday conducted an experiment similar to Franklin's. Faraday lined the exterior of a room with metal foil and charged it with an electrostatic generator. He then used an electroscope, a device that detects electrical charges, in the middle of the foil-lined room. As he had predicted, the electroscope detected no electrical charge within the room. To understand how this works, one must first understand the basics of electricity and conductors. First, conductors are metal objects that have electrons, negatively charged particles, that move around them. In the absence of an electrical charge, the conductor has roughly the same number of positively charged holes and negative electrons. However, if another object with an electrical charge nears the conductor, the positive and negative components separate. If the foreign object has a negative charge, the negatively charged electrons are repelled. If the foreign object has a positive charge, the negatively charged electrons are drawn to that foreign object. This process is called electrostatic induction. With the foreign object present, the positive and negative particles end up on opposite sides of the conductor. This essentially cancels out the field of the external object's charge inside the metal conductor. Therefore, the net electric charge inside the conductive material is zero. And, despite lacking a charge inside the conductor, the opposing electric field blocks out electromagnetic radiation. The extent of this blocking out is dependent on the cage's construction, the size of its holes, its material, and so on. The uses of these Faraday cages are extensive and various. One of the most well-known applications is for airplanes. Airplanes are frequently struck by lightning, which could harm the passengers and quickly damage the electrical components on board. However, this doesn't happen because of the plane's aluminum hull. The charge of lightning strikes and passes over the hull without any inflicted damage. Furthermore, Faraday cages that are the size of rooms are often used as private locations for sensitive information to be shared. Eavesdropping devices cannot penetrate the room. Militaries even use Faraday cages to protect their sensitive electronics from EMPs, which could destroy their vital systems. Faraday cages' usage further range from microwaves to MRI machines. Taking an advantage of a simple rule in physics, Faraday cages undoubtedly play an important part in daily life.